Let's look at a whole problem. Infants, even newborns, prefer to look at attractive faces compared to less attractive faces. In the study, these infants were 1 to 6 days old when they were shown photographs of women's faces, 2 photographs. Previously, a group of adults had rated one of the faces as more attractive than the other. The babies were positioned in front of a screen on which the photographs were presented at 1 to 6 days old. The pair of faces remained on the screen until the baby accumulated a total of 20 seconds looking at one or the other. The number of seconds looking at the attractive face was recorded for each infant. And suppose that the study used a sample of 9 infants, and of course that'll be 8 degrees of freedom, and the data produced an average of 13 seconds for the attractive face with a sum of squares equals 72. Now, we're going to have to reduce that sum of squares, and again, I will never do that to you, but I want to just go through the problem because it's right out of the text. Note that all the available information comes from the sample, and ultimately, the standard deviation will come from the sample. Specifically, we don't know the population mean or the population standard deviation. So the first thing we're going to do is state the hypotheses. Although we have no information about the population of scores, it's possible to form a hypothesis about the value of mu. In this case, the null hypothesis states that the infants have no preference for either face. That is, that they should average half of the 20-second lookings at the 2 faces. So we'll say that the mean looking at time is 10 seconds for the attractive face. And the alternative hypothesis says it's different than 10 seconds. Now, in this case, it's a two-tailed. You'll remember from our conversation in Chapter 8 that we're not predicting that the attractive face will garner more looking time, which is a little bit artificial and kind of frustrating and not realistic, but we have to start somewhere. And I want to start with a two-tailed test, so we'll just say it's different than 10 seconds. But after all the exercise that we went through in Chapter 8, this should really leap off the page as a two-tailed test. And we'll set it at alpha of 0.5 for 2 tails. So our next step is to locate the critical region. The test statistic is a t-statistic because the population variance and standard deviation are not known. Therefore, we need the degrees of freedom. Just 9 infants minus 1 is 8. That's a piece of cake. For a two-tailed test, alpha of 0.5 with 8 degrees of freedom, the critical region consists of t values greater than plus or minus 2.306. Let's check it out. So here's the table. I've got 8 degrees of freedom, alpha of 0.5, two-tailed, bang, 2.306. Looky there, which is like a ton of bricks. I like it. So it's becoming pretty interpretable. As muddy as this PDF scan is, it's still clear enough to be able to be read. And no question, we had 8 degrees of freedom with alpha of 0.5, two-tailed. Can I go ahead and plot that on there? Sure. There's a minus 2.306. Here's a plus 2.306. And here are the critical regions in the t-distribution for alpha of 0.5, degree of freedom of 8. Okay, I like it. And then we go through all this headache, and my problems are simpler, frankly, where we finally arrive at t. So what they did, and what I'll never have you do, is reduce the sum of squares to the variance. But you'll remember from Chapter 4, when we were actually in class together, that was very doable. It was sum of squares over n minus 1, so 72 over 8 is 9. And then, of course, all I have to do, coming down here, to get the standard deviation is to take the square root of 9, which, of course, is 3. That's no problem. So what I'll then do, and of course there's my 3 right there, my estimated standard error is just that 3 over the square root of the sample size, which is 9. 3 over radical 9, of course, is 1. Now, if you wanted to, and I'm less inclined to do it this way, you could also just plug the variance in. And in that case, that'd be 9 over n, and the square root of 9 over 9 is the square root of 1 is 1. Either way you go about doing it, it comes out in the wash. It's no big deal. So what I'll always give you, I'll make this pledge, Mr. Spock's honor, is to always give you S. I really believe in that. Just simplify, simplify, simplify. And here's my T statistic. The infants looked at the attractive face for 13 seconds. Did it say that somewhere? I don't think it ever did. No, I don't think it did. It's just telling us that right now for the first time. So they looked at the attractive face for 13 seconds, and here was mu of 10. And just by chance, we got an estimated standard error of 1, and my t obtained is 3. Well, how does that fit into things? Well, the obtained t statistic of 3 falls into the critical region on the right side of the t distribution. Our decision is to reject the null and conclude that babies do show a preference when given a choice between an attractive and an unattractive face. Specifically, the average amount of time that the baby spent looking at the attractive face was significantly different from, because it's two-tailed. It could have been less than, but it just happened to be greater than, from the 10 seconds that would have been expected. So here goes. And just like before, we're going to plot this out. Here's step 4 continued. Here are my critical values. There's my obtained over here, which is 3. And sure enough, it falls out in that critical region, and it's a slam dunk. We just go ahead and reject the null hypothesis. There's no thinking. This is a no thinker. So no brainers, they call it. So the process is the same. It's just that the math is a little bit different, and the t criticals are just a little extra effort to find from a different table.